Hey guys, today we're going to be talking about wave characteristics and speed. That's in relation to our simple harmonic motion, which we've been discussing. If you remember back in the lab, we had a wave turn out for the graph of the motion for simple harmonic. It ended up looking something like that. So simple harmonic motion was just anything that repeated itself, and waves are things that repeat themselves. So we're going to be studying their properties today. It says a wave is a disturbance, that's the word that goes there in that blank, that propagates from place to place. So propagates just means that it moves, and it carries energy as it travels. Some notable examples of this include sound. Sound is a series of vibrations that move through the air. Okay, so it disturbs the air, and that air vibrates, and then it vibrates all the way over to your ear, and you hear it by it vibrating your eardrum inside your ear. Another good example is light. Okay, so light is made up of electricity and magnetism that are moving back and forth, oscillating in a wave form, and they take energy from one place to another, and that's in the form of light. And then another notable example, one that's already familiar to you, I'm sure, is water. Water carries waves, and it holds energy. You can see that catastrophically through tsunamis. You can see it through surfers when they get kinetic energy from the water. It's a disturbance, a change in the water, and it moves from place to place, and it carries energy as it travels. And the reason that waves are connected to periodic motion, which is the same thing as simple harmonic motion, is because they go through cycles. It's a repetitive motion. Just like the pendulums and springs that were swinging back and forth or bouncing up and down in our lab last class. So today we are going to also be discussing the two main types of waves, transverse and longitudinal. And we're going to be drawing those and labeling them. So you're going to need two sections. You split that gap on your paper there in half. One for transverse and one for longitudinal. I always have to think really hard about how to spell the word longitudinal. A transverse wave is the wave that you would normally think of when you think of a wave. But we're going to need to start off with just an axis, so like a middle line for it to go on, so we can kind of see in relation to things. And then on that axis, you're just drawing a curve. It's like a sine or cosine curve, kind of like the one that we did the other day in the lab. And you're going to need to know different parts about this wave. So the first part is the crest. It's right there at the top. And that is the opposite of the trough, which is right down there at the bottom. The crest and the trough. Okay? You also need to know a thing called the amplitude. Now, the amplitude is the distance from the center line there to either the crest or the trough. So it's from the center, not the total height, not like that. It is only from the center line to a trough or a center line to a crest. Okay, either one. You can go to the crest or to the trough, but that is the amplitude there. It's simply a measure of how big the wave is. Now, we also have a property called wavelength. Okay, so wavelength is the distance from one point on the wave to another similar point on the wave. Okay, so that could be like the distance from one crest to an adjacent crest. That would be a wavelength. You could also do that from a trough to a trough, and that would still be a wavelength. Or you could do it from one middle point to the other. However, you have to do this middle point going the same direction. So this middle point goes up after it, and this middle point goes up after it. So those two could be a wavelength. But this one and this one couldn't, because this one's going up right there, and that one's going down. Okay, so those 2 points are not similar. It had to be this point and that point for your wavelength. So it's easier to measure it from crest to crest or trough to trough. But it's simply the distance from one location on the wave to another location that is the same type. So crest to crest or trough to trough. And they have to be next to each other. One wavelength is from one crest to the next crest. And then we've got the longitudinal wave. So a longitudinal wave looks a little bit different. Usually it's represented by a series of lines or as a spring. I'm going to do a spring because I think it's fun to draw one. So a longitudinal wave starts off really compressed, and then it stretches out, and then it gets more compressed, and then it stretches out, and then it gets more compressed, okay? So we've got little bunches here, here, and here. They're bunched up. So the anatomy of this one is kind of similar to the transverse. What we would call a crest on the transverse is actually where all of these things are bunched together, and that is called a compression. That is where everything is squished close together. It's compressed. And the opposite of that, which is kind of like a trough for the transverse wave, is what's called a rarefaction. That's rarefaction. So where it gets super spread out. So I guess you could say it's rare there. Okay, so a compression is where it's squished. A rarefaction is where it's all spread out. And the wavelength for a longitudinal wave is the same idea as with the transverse. It's the distance between two similar points. So the distance between one compression and another compression would be its wavelength. Or you could say the distance between one rarefaction and another rarefaction would be a wavelength. So those are your options there. You can measure compression to compression or rarefaction to rarefaction, but it's still simply the length of the wave. Now, the amplitude for a longitudinal wave is a little bit odd. The amplitude isn't a height like it is with the transverse. It's not as easy to measure. But the amplitude is basically how compressed it can get. Okay, so if it gets super compressed, then that's a very high amplitude wave. If it's not very compressed, then that's a low amplitude wave. And that's talking about at the compression points. So I'll show you some animations of that in a second so we can see how it looks. So here I've got two animations. I've got one of a transverse wave, one of a longitudinal wave. And you guys definitely saw these when you did your waves simulations activity a few days ago. This top one is a transverse wave. The way you can tell it's a transverse wave is that the particles are moving up and down. If you follow an individual blue particle, it moves up and down while the wave is moving to the right. Now in your longitudinal wave down there, the wave is still moving to the right, but the particles themselves are going back and forth left to right, okay? In the top one, they're going up and down, and the bottom one, they're going left to right. This top one is transverse, and the bottom one is longitudinal. Now, it's really easy to see the amplitude on the transverse one. Okay, the amplitude is just from the center, which is about like that, to the edge. So the amplitude is kind of small on this one. It's something like that. The longitudinal one, you can see is like how close these are compressed. Okay, so that's the amplitude there, is how closely those are compressed. Something that's lower amplitude would not have quite that much compression at one of the compressive points. But there's a compression here. In the middle here is a rarefaction. You see them kind of spread out that way. So our top is transverse. Our bottom is longitudinal. Now, with these, we do have period and frequency. So I'm going to get up the same animation and we'll look at it. So here we have just the transverse wave. If we're thinking about the period, that would be how long it takes for one cycle of this wave to go. So when you're looking at the period, you really want to settle on one point. I'm going to look right here, okay, right there. And I would start timing when it's at the bottom and then see how long it takes for it to go one full up and down in that cycle. Okay, so I would start timing like now. Watch that one particle go up and stop when it comes down, okay? So that would be finding the period. Now, if we were going to find the frequency of this, what we would do is we would see in 1 second, we time for 1 second, how many wave cycles go past that one little point. So I would go like 1 Mississippi and say that was about half of a wave cycle and went all the way up, but it didn't come back down. So that would be a frequency of 0.5 hertz. So measuring the period and frequency on a wave is just like doing it as we did for the pendulums and for the springs, just you'd be looking at one specific point on the wave. Now, if you flip over to the back of your notes, you're going to see a little bit about wave speed. So waves can go really fast, they can go really slow, and really the only determining factor is whatever material that the wave is in. Materials matter a lot. Waves travel really fast through solids. They travel a lot slower through liquids and gases. So that's why you can hear a lot better through solid objects rather than through the air. Like when you put your ear on the door to listen to somebody's conversation beyond it, you can hear that, whereas you couldn't hear in the air because the solid is a much better conductor than the gas for the waves. So the material that the wave is traveling through is called a medium. You're going to need to know that word. The speed only depends on the medium, but the speed and the period/frequency of the wave determine how long the wave actually is. So how close those troughs and crests are, like in literal physical space, how far apart they are in meters. Wavelength is a literal length. And in order to find this wavelength, we need one equation. That equation is for wave speed. It says the wave speed, which is a v, and is measured in meters per second. That equals lambda. Lambda looks like an upside down y. That is for wavelength, which is measured in meters, times the frequency. Okay, so velocity or wave speed equals lambda times f. That's frequency, which is in hertz. But this can also equal lambda divided by t. So lambda is still wavelength, but t is period, which is measured in seconds. So as always, you're going to choose the sections based on your given, but this is your main equation. Velocity equals wavelength times frequency, which also equals wavelength divided by period. We'll see how to use that here in our next example. It says, or asks, what is the speed of a wave with a period of 0.02 seconds and a wavelength of 0.3 meters? So we go look at our givens. It tells us the period is 0.2, so that's a capital T for period, equals 0.02 seconds, and a wavelength of 0.3 meters. So wavelength is the lambda, that's 0.3. Question is, what is the speed? So that's the velocity. Oh, that's a really bad question mark. I gotta draw it again. Okay, so now we're gonna look at our equation and decide which things we need. For the v, we're looking for v, so we definitely want that part of it. The lambda times f. We have the lambda, so that's good, but we don't have the frequency, so we probably do not want to use that section. And then the last section, we've got the lambda. We also have the t, so that's going to be what we want to use. Velocity equals lambda divided by t. We'll plug the stuff into that. So that equals 0.3 divided by t was 0.02. And then you get to type that into a calculator. And when you type that in, you're going to get 15, and velocity is measured in meters per second. So your wave speed here is 15 meters per second. Now our next example asks what the frequency of a wave is with a wave speed of 10 and a wavelength of 0.3. So once again, we're going to write down our given information. We've got a wave speed of 10, so that's a velocity. It equals 10, and a wavelength of 0.3 meters. So that's a lambda. That's 0.3 meters. Question is, what's the frequency? So we've got to choose what parts of our equation we want. I'm going to write it again here because it's off the screen. You don't need to write the whole thing. But I'm going to just show you so we can choose the correct pieces of it. All right, so we have the velocity over here. So that would be a good section to use. We have lambda, and we're looking for f, so that's also a good section to use. Our last section, we have the lambda, but we don't have the period. So we're going to not use that last one. We're just going to use that the velocity equals the wavelength times the frequency. That is v equals lambda is 0.3 times frequency, which we don't know. Oh, I forgot to plug in the v. That is 10 there for the velocity. So we're going to do 10 divided by 0.3 because we got to get rid of that 0.3 so we can have the f. So then you got to do 10 divided by 0.3, which is 33.3 repeating. So we'll round that off to 33.3. Frequency is measured in hertz. Okay, so that's saying the wave is going to go by 33.3 times every second. That's a pretty quick wave. And then our last question here, the last example, it says, what is the period of a wave with a wave speed of 343, that is the speed of sound, by the way, and a wavelength of 4 meters. So we've got a wave speed of 343, that is velocity. We've also got a wavelength of 4, and we're looking for the period. So I'm going to write the equation once more so we can choose sections. We have the velocity, so we're going to want that section. We have the lambda, but we don't have the frequency, so that goes by. In our next section, we better have everything because we need another section. We have the lambda, and we're looking for the period. So that one's going to be good to go. I'm going to erase this so I can rewrite it, but we're going to do v equals lambda divided by t. Velocity equals lambda divided by period. And then we're going to plug stuff into that. The velocity is 343. That equals lambda, which is 4, divided by t, which is the period. So here's where we come to an algebraic issue. We need to solve that for t, but t is on the bottom. So when you're solving for something that's on the bottom of the fraction, you have to get it out of the bottom. There's several ways to do this. You can flip the fraction and the other side. You could cross multiply. You could do butterfly method if you know what that is. It doesn't really matter which algebraic method you use as long as you get the same answer because you're doing correct algebra. So the way I'm going to show you is to get t out of the bottom. It's currently being divided. So what we're going to do is multiply both sides by that t. When you do that, these ones cancel. So you end up with this other equation. I'm going to go ahead and erase those that got canceled. You end up with this that says t times 343 equals 4. So then what you can do is you can divide both sides by 343 so that those cancel, and you end up with 4 divided by 343, which is very small number, 0.0116, or it rounds to 117 seconds. So that's saying it takes less than 2/100ths of a second for this wave to go through one cycle. That is what the period means. That's the number of seconds it takes for it to do one cycle. So that's also a very quick wave going there. Now, solving for period is the worst algebraic option. We don't like it, but we do what we got to do. So you have a practice to work on. It is 8 questions long. The answers to it are posted in Classroom, so you can be checking yourself as you go to make sure you get all those right. There is a quiz over this. It covers the wave characteristics from the notes. It covers wave speed calculations, and it also covers some of the period and frequency calculations that we did last class, which was on our lab day. Those equations are up on the board if you need to refer to them. So you'll finish your practice up, those 8 questions. You're going to show it to our wonderful sub, whose name I do not know. And that sub is going to give you the password for the quiz, which you should take before you leave today. All right. I'll see you guys next week. Hope you have a great weekend. Be safe, and see you next week.